Okay, so let's do an exercise together. So I've used the best of my artistic skills to draw this with a pen. You may complain all you like. I think it's brilliant. This is a rigid bar, and at its two ends there are two rollers, a roller at B and a roller at A. The roller at A can only move horizontally. The roller B can only move vertically. And I've used theta to denote the angle of this whole bar in relation to sort of like the x-axis. So here, talking about axes, here is the coordinate system we're going to use. I goes horizontally, j up. Positive spinning is from I to j, k comes out of the page. And g in the center there is the center of mass. So the interesting thing about this question is we're going to imagine that this is part of some mechanism, and we're going to apply a force at A. We're going to ask ourselves, how does this force, how much force, this vector force here, how much will it accelerate the change of angle, theta? So imagine the bar is initially at rest, and then suddenly this force appears. Okay? So here's a little blah blah of I just said. The bar has two roller joints. It's just as I explained. The bar was at rest. Let's find the angular acceleration in terms of the force. So we're going to have to use everything we've learned up to in kinematics and kinetics to do this question, but it's pretty cool. So the first step we do is we use just the kinematics. It means the movement of things. We look at that picture and we try to relate the relative movement between the different points just through pure geometry. So we don't need to think too much about conservation laws. So the first thing we do is that the acceleration of the roller A can be written as the acceleration of the roller B plus the angular velocity, the angular vector cross product with the vector that goes from B to A plus what would be the effect of sort of the centripetal force. Now this term I'm going to make 0 because I'm going to make omega 0 because the bar is initially at rest. It's not moving, so its velocities are all 0. And that makes the problem a bit easier. So now I'm going to rewrite these vectors in terms of their component forms. As the roller A can only move horizontally, its acceleration can only be horizontally, so I've written that as a scalar, just a number, AA times the vector I. Similarly for the roller B, it can only move vertically, so I've written that its acceleration is only the vertical direction. I've substituted the angular acceleration vector in the direction k, as we always do. And here, if we look at the geometry, we can rewrite the vector that goes from B to A like so. So in case you need a reminder, why is it like that? Let's go up and have a quick look. To go from B to A with the angle theta. This angle theta is the same angle. You could put this angle down here between the from B to A and the x-axis, and then it's literally the definition of cosine and sine that the height of this whole thing is going to be sine of the angle times the length r. So I'm not using the numbers here. I've written that the halfway point is 0.6 meters, but I'm just going to use, I think it actually looks easier to use just r as the full length of the bar, okay? So then to go from B to A, it's just r cosine theta for the I direction, sine theta for the j direction. Okay, let's move on. So I've just substituted. So now we just use how to take cross products between k and I, k and j. So k cross product with I gets you j. K cross product with j gets you minus I. So that's all I've done here. And then if we equate the I terms with each other, so A of I has to equal the I term over here, which is minus alpha r sine theta. Here you go. And you equate the j terms, so the AB has to equal minus this here because there's no j term on the left. We can work out what these accelerations of the rollers are in terms of the angular acceleration. So we're off to a good start. And we imagine that we know the length r because we know the length of our bar, and we know theta because we sort of know its position, its initial position. Okay, so remember that alpha is the thing we don't know in terms of f. Now, because we're going to use the conservation of angular momentum, it really helps to write things in terms of the center of mass. So first we're going to write the acceleration of the center of mass relative to b. So it is going to equal to b plus the angular acceleration of the body cross product with the vector that goes from b to g, actually. So I've written it as from b to a over 2 because that is the same thing as the vector from b to g. I've just written it in a way that is similar, is the same way we already found this vector before, so we just substitute it in here and do the same thing, similar thing we did up there, and we will arrive at here after cancelling some things. Okay, now that we have the acceleration of the center of mass and the acceleration of the other things, we can now use the conservation laws to figure out to relate the forces to these accelerations, because that's what we want to do here. We've got a force on roller A, we want to relate that to acceleration, angular acceleration. So here I think this drawing maybe is a little bit clearer. I'm still missing R. I think I forgot to write that R is the length from B to A. So here goes. Now we're going to write this vector force F that's on A as F times I, because it's directly along the I direction. It wouldn't make sense not to be along I direction because this whole thing is constrained. So this is when it gets a little bit like you need to go to university to solve this kind of problem, and somebody who didn't do this course wouldn't be able to. You've got to realize that because A is trapped along the I direction, that means that there's a force, Fa, that makes sure that it stays trapped. So if it tries to move up, the roller, the structure that the roller's on, this rolling joint, will place a force to stop it from moving up. Similarly, in the same way for B can only go up and down, so when we do apply a force here, the bar will try to move in other directions, but the roller joint will stop it by placing a force Fb. So we don't know who these forces are. In fact, these forces change depending on how you force this whole system. So I've just written that this vector Fa, or the only thing I know about it is that it's going to be necessarily in the vertical direction, because it's trying to keep this roller from moving in the vertical direction, and the force Fb is necessarily in the horizontal direction because it's trying to stop the joint Fb from moving in the horizontal direction. So now we're ready. Once we've drawn a free body diagram and we've drawn all the forces on it, and we know sort of the angle and the geometry, and we've already done the kinematics, we're now ready to apply the balance laws. So let's do that. So first we're going to do balance. Well, we can do both of them, balance of linear and angular momentum. But let's start with balance of linear momentum. So all that means is you just sum all the forces together, and all those forces together have to equal the acceleration of the center of mass times the total mass. So we've already figured out this thing here. Before it was minus r alpha over 2 times sine theta I vector plus cosine theta j vector. And then we've already substituted on the left the component forms. So now again we equate the I and the j terms. If you equate the j terms, you'll find that Fa of j has to equal minus r alpha over 2 cosine theta of j. There you go. Same thing for the I term. Now for the slightly trickier one, maybe is conservation of angular momentum. Now because we're using because we can choose where to take this conservation of angular momentum. You can take it about anything you want. We could have chosen to take conservation of angular momentum about B, and that would be, understanding how momentum is preserved about B, about A. You can choose wherever you want, but actually the result will be the same. As long as you carry out the algebra properly, the result is the same. So we choose the easiest one. We're going to choose to look at conservation of angular momentum about G. So if you remember from the lecture, we had an origin O. That origin now is going to equal G, because that makes everything easier, because that means conservation of angular momentum is just the moment of inertia about the center of mass times the acceleration, the angular acceleration, equals all the applied torques. So the applied torques, we need to see where the forces are applied. You see that F and FA are applied in the same position. So we need to take the vector that goes from G to A and cross it with that force. So the vector from G to A crossed with all the forces plus the vector from G to B crossed with the force at B. So these are the sum of the torques. Okay, so the vector from G to A is the same thing as the vector rho G actually, and it's just that. And then I just substitute the forces here, and we already know who FA and FB are in terms of alpha and F. And here I've substituted the vector from the G to B. So it's basically minus the vector from G to A, and that makes sense, right, because of the symmetry. And I've substituted the force FB here. Now, if you take the cross product of all these things, and here's a little tip, I crossed with I is 0, J crossed with J is 0, I crossed with J is K, and J crossed with I is minus K. And if you use all that and you sum everything together, it all gets pretty simple actually because stuff cancels. So take note, that's after a bit of simplification, and this is what you get. Okay, great. So where are we now? We wanted to relate F to alpha, right? We've made great headway. We found out what all the other forces are in terms of F and alpha. And we've managed to boil it down to an equation which is just the moment of inertia alpha equals this stuff on the right. So really, the last thing that remains for us, because we know who the mass is, we know who R is, the last thing that remains is the moment of inertia. So if you go to your table of formulas, you'll find that that's in the tab of exams in Blackboard. I've put a formula sheet that you can have. Using all you need to do is look up the moment of inertia of a slender rod around its center of mass, and that equals this here. You can do it yourself. It's quite an easy integral to do. If you look it up on YouTube, there's people who are doing it for you, and it's really straightforward. So now we're just going to substitute this up there, and what we're going to, well, first I'm summarizing. So here, this is the moment of inertia times alpha, so now I've just rewritten, I've just substituted the moment of inertia here, and I put alpha. This now equals the right-hand side of the equation above, so just put that down here. And this is our final equation. All you need to do now is rearrange alpha in terms of F. So alpha equals minus 3F sine theta over mr. And we're done. Okay, I know it wasn't super easy, but the result is very simple and easy to interpret. In fact, I recommend you do try and interpret this. You choose different angles theta, choose a positive or negative force, see if it makes sense what the angular acceleration should be. And I assure you, it does.